This is an example of data that's been acquired on an instrument that has been calibrated using the NPL software to work out the transmission function. And we will now demonstrate using relative sensitivity factors that are based on Schofield cross-sections corrected for escape depths how we can obtain useful information about a material. Now this material is graphene oxide. So first of all, we've looked at the survey spectrum and we've calculated the relative proportions of oxygen, carbon and a small amount of nitrogen based on the survey spectrum, and we're getting 2 to 1 carbon to oxygen. And that's an interesting result in itself. So let's just verify that and show how we can display it using an annotation option. And what we're doing is we're creating a formula to illustrate from the region intensities what the relationship currently is. So we've got 2 carbon to 1 oxygen on the basis of the survey spectrum. So having used the survey spectrum to get a first idea of what might be there, we'll now look at the high resolution spectra. And because the high resolution spectra have also been calibrated, we expect to get similar results between the regions from the high resolution spectra as we do from the survey spectrum. Without the calibration, this would not be true. So we'll begin by just simply creating regions and using the same relative sensitivity factors, and we'll use an annotation option where we can compare intensities between 2 VAMAS blocks. So we go to the quantify option, using regions, we'll see that we do still have the 2 to 1 relationship, which is simply because we have calibrated the instrument using the NPL software, so the response to the change in the pass energy and any other lens modes have all been allowed for by the NPL software. So now, having looked at the regions, let's investigate this a little bit further using a component model. And this is graphene oxide, so we would expect a peak bonded to oxygen in this carbon 1s, and then we'd expect to see other peaks perhaps, and we'll create a peak model where for one particular of these peaks it looks very much like it's the C bonded to oxygen peak. That's probably the sp3 peak, and now this one here is the C bonded to oxygen peak, and then we have some satellite peaks. And if we go through this peak model and then fit these peaks to the data, we can then do a comparison against the signal that we've got from the oxygen. And again, this is only possible because we've calibrated using the NPL software, and it is giving us a quantification from the survey and the high resolution spectra that are consistent. So now if we use another quantification option that lets us compare components against a region, the region is coming from the oxygen, we can now see that the breakdown looks like we've got about 1 to 1. The peak model is involving 5 peaks, so just allowing them to fit to the data, it's not surprising it's not perfectly 1 to 1. So let's do a little experiment here, and rather than allowing a free peak fit, we will constrain the CO component to be the sum of all of the other components, because we saw from the survey and from the regions on the high resolution spectra it's about 2 to 1. So this is trying to work out, is it feasible that it's a 1 CO bond to all other signal. And yes, you can see now that this has produced a reasonable fit, and you have a 1 to 1 relationship, so this looks like a feasible solution.